Hey guys, this is Mrs. Harbin, and this is Algebra 1. Today we're going to be looking at section 3.5, which is about percent change and error. Our biblical integration for this unit continues to be that Jesus set the highest standard for us to live up to by sacrificing all in service to his Father. We should be willing to do no less in our commitment to working for him. Now that might seem, why are we talking about Jesus' sacrifice when we're talking about math? It's the standard of doing our best and giving our best so that we can do the work that God has for us to do. And that includes things that might seem as unimportant to you as math and percentages. But in the command that we're given, it's not do your best unless it's, boring, unless it's uninteresting, or do your best only in spiritual things. It's do your best in everything. And that includes what we're working on today. Our lesson objective for today is that you, the student, will find the percent change when a quantity increases or decreases, and find the experimental error and the percent error of a measurement. Let's take a look at some definitions. When we talk about percent change, what we're looking at is the amount of change compared to the original amount. You should notice that that is a ratio. So we might want to know the percentage of when things change, like if a price goes up or something's on sale, and we want to know if it's a good deal or not. So let's take a look at this example. An increase from $3 to $4. Not too long ago, this is maybe the price of gas. It was $3 a gallon and it increased to $4. In order to find the percentage of increase, we know it's $1, but let's use this percent increase formula, which was the amount of change over the original amount. The amount of change was $1. The original amount was $3. When we multiply that, which is a decimal, by 100, we find out that our percent increase was approximately 33%. It's going to be 33.3 repeating, so we're going to say approximately 33%. So when gas increased from $3 to $4, it increased by 33%. Now let's take a look at the decrease. Let's say it was $4 and it decreased to $3. We know that's a $1 decrease. Again, our amount of change is still $1, but our original amount is not 3. Our original amount was 4. Well, 1 divided by 4 multiplied by 100 is a 25% decrease. Now you may be thinking, shouldn't it be the same if it went up by 33%? Shouldn't it go down by 33%? Remember that we're not describing the amount of decrease. That was $1. That's the same. We're comparing it to the original price, the price that it increased or decreased from. And so the percents are not going to be the same since they're based on a different original price, whether $3 or $4. All right, let's take a look at the amount of change here. Our amount of change given, this is in your book on page 117. The amount of change is 144, and the original amount was 1,056. This is looking at some voter information. Last year, 1,056 people voted in the city election, and this year only 912 voted. That's a decrease of 144 people. So we want to find the percent of decrease. Taking our amount of change, 144, divided by our original amount, 1,056, and multiplying that by 100, we find that our percent of decrease was 13.6%. That means that 13.6% fewer votes were cast this year than last year. So if I were working on a voting committee or working for a specific candidate, I might want to then think, what can I do to increase the number of voters for next year to get people out to vote and voice their opinion? Now, in general, an increase of X percent implies that the new amount is 100 plus X percent of the original. So an increase of 5% would be 105% times the original. A decrease of X percent implies that the new amount is 100 minus X percent of the original. So a decrease of 5%, for example, would imply that the new amount is 95% of the original. So let's take a look at example 3. In the city of Woodridge, is projected to grow by 7% over the next decade, and its current population is 35,000. If it's going to grow by 7%, we need to know how many people should be planned for at the end of the next 10 years. Now, this is a really important question. City planners use information like this all the time when they're trying to decide what roads to work on, where to put housing developments, or what schools need to be built. They look at the projected increase and plan accordingly. So if you're interested in going into city planning as a career, this is a skill that you would need. So our current population is 35,000, and we know that there's a projected 7% increase. So we know it's going to be 107% of our original population. 100%, that means keeping what we already have, and then adding another 7% increase. Well, putting that into our calculator or calculating that mentally, 107 as a decimal is 1.07 times 35,000. Gets us to 37,450. So we need to plan on an increase of 2,450 people. In example 4, a runner is able to decrease his time in the marathon by 13% to a time of 2 hours and 47 minutes. Written in all minutes, that's 167 minutes. We want to know what his previous time was. So his current time is 167 minutes. There was a 13% decrease, which means 167 is 100 minus 13% of his original number, or 167 is 87% of his original time. Writing that as a decimal, we have 0.87. 167 divided by 0.87 gives us an original time of 192 minutes. Putting that back into hours and minutes, we get 3 hours and 12 minutes. So he was able to reduce his time by quite a bit. Let's look at another definition, percent error. Percent error is used in scientific experiments, medical experiments, any experiment where you are measuring things mathematically, quantitatively, and you want to know the percent of error that you've made. We're not perfect, and we know that there is a chance for error. To discover percent error, we're going to use this formula. The absolute value of the experimental value minus the known value divided by the known value times 100. The numerator, which is inside the absolute value bars, is sometimes called the experimental error, taking the value that you get in your experiment minus what we know the value should be. All right, in example 5 in our book, Jonah determines the density of copper to be 8.83 grams per centimeter cubed. But the known value of copper's density is 8.96 grams per centimeter cubed. Determine Jonah's experimental error and his percent error. So this is what he finds, 8.83, but the known value is 8.96. Okay, using our value, we know experimental error is experimental value minus the known value. So 8.83 minus 8.96, that gives us an experimental error of negative 0.13. To find the percent error, we divide that by the known value. So the absolute value of negative 0.13 divided by 8.96 and multiply that by 100. And we find out that his percent error was approximately 1.5%. Now, if we're doing measuring of chemicals or measuring of medicines, we want to make sure that we're being very precise and very specific. So this percentage of error can tell us how precise we are in our actual measurements. Another definition that we need to know is percent difference. Percent difference, and this will help us find the difference between two different things. So we're going to take our first value minus our second value, divide it by the average of the values, or average the values to divide by 2, and multiply that by 100. This formula is helpful if you don't have a known value to compare the results to. Maybe we're doing an experiment and it's involving something that we don't already know. And we do this experiment a couple of different times to find out the difference in our results between each time. So in example 6 in our book, Suzanne is asked to determine the volume of a cylinder. Using water displacement, she arrives at an answer of 15.64 centimeters cubed. And then she measures the cylinder's dimensions and calculates the volume to be 14.01. So that's two different values for volume. The average of those values is 14.825. Using our formula, this is on page 119 of your book, we're going to take our first number, 15.64, minus our second value, 14.01, and divide it by the average of 14.825. We'll multiply that by 100 to get our percent difference. And when we do that, we find there's an 11% difference between the measurement using water displacement and the measurement using dimensions. Today we found the percent change when a quantity increases or decreases, and we found experimental error and percent error of a measurement. We also found the percent difference of multiple measurements when a known specific measurement is not known. Again, this is one of the most valuable things that you will learn and that you'll apply in math, knowing how to use percents. So if you have any questions, be sure to ask me next class.